Hello mathematicians, thanks for joining me as we look at a function from z cross z to z cross z. Namely that we're going to map m comma n to 5n plus 4n comma 4n plus 3n. And what we want to show today is that f is a bijective mapping. And so that means that we're going to have to show that it's a well-defined mapping, that it's one-to-one, and that it's onto. And so as we go through that, we'll go through it piece by piece until we're finally able to show that f is bijective. The first thing we want to do is we want to check that f is a well-defined mapping. That is that for everything in the domain, it's mapped to exactly one thing in the codomain. So that is, if I start off with an element in the domain, say m kind of n, I want to make sure that this ends up getting mapped to exactly one thing in the codomain. And so really what I'm asking here is that this is going to get mapped to this point here. What I need to know is that every time I map this in, I'm going to get out an answer, and I'm going to get out exactly one answer. So what I'm doing here is I'm just saying, well, if I take 5 times an integer, m, I'm going to end up with an integer. If I take 4 times an integer, I'm going to end up with an integer. And if I add 2 integers, I end up with an integer. And now each step along the way, there's no way to get 2 answers each time I got out 1. So this term would be uniquely defined. If I do the same thing for this term, 4m plus 3n, again, is going to be a uniquely defined integer. So what we're checking here is to make sure that my image, 5m plus 4n and 4m plus 3n, is going to be uniquely defined in z cross z. That is, I get out one and only one answer. And in this case, I do. So now, as I write that up as a proof, the important thing here is really just checking to make sure that makes sense. So I would say for a proof for well-defined is that let m and n be in z cross z, then for m plus 3n and 5m plus 4n are uniquely defined integers. Now, they are uniquely defined by definitions of how we define the integers. So there's nothing really to prove here other than the check to say that, well, if I multiply integers, I get one answer. If I multiply integers, I get one answer. If I add integers, I get one answer. So all I'm claiming here is, okay, I know that each of these are uniquely defined. Therefore, the ordered pair, 5m plus 4n, comma 4m plus 3n, is uniquely defined in z cross z. Hence, we have that our function f is well defined. That is, for everything in the domain, I have exactly one thing in the codomain, where the thing in the domain gets mapped to the thing in the codomain. Now that we have that f is a well-defined mapping, we want to show that it's an onto mapping. So what does onto mean is that if I take anything in the codomain, I can find something in the domain which gets mapped to it. So what we have to do here is we have to let something be in the codomain, which in this case is z cross z. So let's just say x comma y is in z cross z. What I need to do is I need to find an m comma n that gets mapped to x comma y. And so in order to do that, what I really have to do is I have to find, well, f of mn is going to be 5m plus 4n, 4m plus 3n, and so I have to find an m and n such that this is equal to xy. Now, since we have an ordered pair is equal, that means that the terms are equal. So what we would have to have is 5m plus 4n is equal to x, and 4m plus 3n is equal to y. And so what I get is a system of equations with 2 variables and 2 equations, and I'm going to have to solve for m and n. And now I'm going to treat these like constants, but I'm going to solve for m and m in terms of x and y so that I know which mn I should choose in order to get mapped to the point xy. Now that I'm left with these 2 equations, what I have to do is figure out how to solve this. And well, there are a lot of ways to solve this. And so how we could do this is notice that, well, system of equations, I can use substitution, I can use elimination by addition, I can use matrices, or any other technique. I'm going to end up using matrices here because I feel like they're the most convenient once you get used to them. So I would like to give you some practice working with them, but if you'd like to use another technique, that's fine as well. Alright, so now if I'm going to solve this system of linear equation using matrices, the idea is that I'm going to write the coefficient matrix where the first column is m, second column is n, third column is going to be x, and the fourth column is going to be y. So if I pull the coefficients off, I get 5, 4, 1, 0, because there's 0 y's up here. And then I get 4, 3, 0 y's and 1, or 0 x's and 1 y. So I have the augmented matrix 5, 4, 1, 0, 4, 3, 0, 1. And now the goal is to row reduce this into equivalent matrices so that I get out equivalent systems of equations so that in the end I know what m and n are, and then they're easy to find from the system of equations. So what type of operations can I do is, well, I can multiply a row by a non-zero constant. I can multiply a row by a constant and add it to another row. And so I can also take those and any combinations of those in order to get out equivalent matrices so that this works out. Now, there are quicker ways to do this, but what I like to do is when I'm working with matrices, I always use the same technique as I work my way around counterclockwise, starting from this corner up here. And what I want is I want this matrix on the left to look like 1, 0, 0, 1. So that's my goal, is to get a 1, 0, 0, 1 over here. And so I'm going to do this piece by piece so that regardless of what matrix it is, I can always follow the same steps, or the same algorithm if you like, in order to get out a row reduced form here. So now the first thing I want is I want this to be a 1. So the way I can make that a 1 is I'm going to multiply by 1 over this number times the first row. So I'm going to get 1/5 times row 1, and then I'm going to plug that into row 1. And what I get is the new matrix where the second row stays the same. And the first row becomes 1/5 times 5 is 1, 4 times 1/5 is 4/5, 1 times 1/5 is 1/5, 0 times 1/5 is 0. So I have the matrix 1, 4/5, 1/5, 0, 4, 3, 0 is equivalent to my original matrix. Next, what I want to do is I want to work my way around. I got the 1, so now I need a 0 here. So in order to get a 0 here, I'm going to take -4 times row 1, add that to row 2, and plug that in for row 2. So if I come over here, what I'm going to get is the first row stays the same, so I get 1, 4/5, 1/5, 0. And then I'm going to take -4 times 1 is -4 plus 4 is 0. And then I'm going to get -4 times 4/5 is -16/5. So I'm going to write that one down so I can remember it. And then I'm going to add that to 3. And so if I take -16/5 plus 3, that's -16/5 plus 15/5 is going to be -1/5. Then I'm going to take, again, -4 times 1/5 plus 0 is -4/5. And then I'm going to take -4 times 0 and add that to 1. So 0 plus 1 is just 1. So I'm left with my new matrix, 1, 4/5, 1/5, 0, 0, -1/5, -4/5, 1. So now I have a 1 in the first row, first column, and then I have a 0 in the second row, first column. And next I'm going to get a 1 in the second row, second column. So in order to do that, I'm going to divide by -1/5, which means multiply by -5. So I'm going to take -5 times row 2 and plug that into row 2. So I'm going to end up with 1, 4/5, 1/5, 0, because the first row stays the same. Second row becomes 0, 1, 4, -5. So I now have a matrix where I have 1, 0, 1. The last thing I need to do is get a 0 up here. So in order to do that, I'm going to take -4/5 times row 2, add that to row 1, And I'm going to be left with the matrix 0, 1, 4, negative 5 because the second row stays the same. And then negative 4/5 times 1 plus 4/5 is going to be 0. Negative 4/5 times 0 plus 1 is 1. Negative 4/5 times 4 is going to be negative 16/5 plus 1/5 is going to be negative 15/5 is negative 3. And negative 4/5 times negative 5 is 4. 4 plus 0 is 4. So I end up with the matrix 1, 0, negative 3, 4, 0, 1, 4, negative 5. So now I can use that to convert it into an equivalent system so that I can find what m and n should be. Alright, so I've converted my matrix back into a system of equations, and what we realized was that this system of equations is equivalent to this system of equations. So if I want f of m comma n to be equal to x comma y, what I should do is choose m to be negative 3x plus 4y, and n to equal 4x minus 5y. So now that I know what I should pick m and n to be, and I'm now ready to find or give a formal proof that indeed f is an onto mapping. Alright, so to give our proof of onto, what we need to do is we need to say let x and y be in the codomain z cross z. Now, instead of having to remember this, I wrote it down from what I had before, but I said that, okay, well note that negative 3x plus 4y comma 4x minus 5y is the point I wanted to pick. And I do want to point out that negative 3 times an integer plus 4 times an integer is again an integer. 4 times an integer minus 5 times an integer is again an integer. Therefore, we can note that this is indeed in z cross z, or that is, it is in the domain. Now, from there we would find that now we can say that f of negative 3x plus 4y comma 4x minus 5y is equal to, well, we know f is this function, so what we're going to do is we're just going to say that this is going to be equal to 5 times m is the first term, so that's negative 3x plus 4y, plus 4 times n is the 4x minus 5y. And then we get 4 times m is negative 3x plus 4y. And then plus 3 times n is the 4x minus 5y. Now our goal, remember, is to get x, y out. So what I need to do is just simplify this. In order to simplify this, what I'm going to get is negative 5, or negative 3 times 5 is negative 15x plus 16x. Negative 15 and 16 is 1x, so I'm left with x. Now here I get 20y, here I get negative 20y, so those cancel, so I'm just left with x. If I look at this one, I get negative 12x plus 12x is 0. I get 16x minus 15, or 16y minus 15y is just y. So indeed, f of this term is indeed equal to xy. So therefore, for every x and y in the codomain, there exists something in the domain that gets mapped to that thing in the codomain. Hence, f is an onto mapping. Alright, so now that we want to show that our function is one-to-one, what we want to show is that, well, if we have mn and xy are in z cross z, where the function of mn is equal to the function value of xy, this has to mean that mn is equal to xy. And this means that, again, it would be one-to-one, because if two distinct things cannot get mapped to the same point, because if two things got mapped to the same point, they'd have to be the same to begin with. So now, in order to prove this, what we have to do is think about, well, what does this look like and what does this look like? And so this would mean that 5m plus 4n, comma 4m plus 3n is equal to 5x plus 4y and 4x plus 3y. And now it'll be a while before we get here, so I'll erase that for now. But the idea is that if the ordered pair is equal, that means the terms are equal. So I'd have to get 5m plus 4n is equal to 5x plus 4y. and then I'd have to get 4m plus 3n is equal to 4x plus 3y. Alright, so now what I have again is a system of equations that I want to simplify so that I can show that m is equal to x and n is equal to y. And the way I'm going to do that is, again, I'm going to use matrices. So now, as I go through this, I'm going to have to set this coefficient matrix, augment it with this one. I'm going to reduce it and get an equivalent system of equations. So my augmented matrix is 5, 4, 4, 3, 5, 4, 4, 3. And so if I start row reducing this, I'm going to use the same process I did before. And I'm going to try to turn this into a 1, 0, 1, 0 and see what's left over. And so I would divide by 5 and I'd get 1 4/5, 1 4/5, 4, 3, 4, 3. And so I just took row 1 divided by 5. Then I'm going to take -4 times row 1, add that to row 2, and plug that into row 2. And so what I'm left with is the first row stays the same, 1 4/5, 1 4/5. And then -4 plus 4 is 0. -16/5 plus 15/5 is -1/5. And then -4 plus 4 is 0. And -16/5 plus 15/5 is -1/5. Now again, what I have is I have a 1 and 0, so I want to turn this one into a 1. So I'm going to take -5 row 2 and plug that into row 2. So what I'm going to be left with is the new matrix, 1 4/5, 1 4/5. And then I get 0, 1, 0, 1. So I should have these augmented. The last thing I need to do is I need to get rid of this 4/5. So I'm going to take -4/5 times row 2, add that to row 1, and plug it into row 1. So what I get is 1, 0, 1, 0, 0, 1, 0, 1. So now if I write this as an equivalent matrix or equivalent system of equations, what I get is this just says that m is equal to x and n is equal to y. Now, since m is equal to x and n is equal to y, that implies that n is equal to x, y. So what I get is that if f of mn is equal to f of xy, we do indeed get that through these calculations that mn is equal to xy. Now, I erased them along the way, but the idea is that if I had left all those calculations up, that actually would be the formal proof, is just write these all out, show them that m has to be x, n has to be y. Therefore, we do have that f is 1 to 1. And since f is now 1 to 1 and on to, f would have to be a bijection. And so we have now finished our proof that f is a bijection from z cross z to z cross z. I do want to point out that we could also show that a function is a bijection by showing that it has an inverse function. And so to find the inverse, we just do a lot of the same work we did before, where we find how to go backwards. And then if we find the inverse, we can show that the composition of the two functions is the identity mapping, in this case on z cross z. And then we would have that automatically means that f is a bijection. If you'd like to see that worked out, please visit the written post below. But because I wanted to work through how to do these each step at a time to give us a little bit more practice with one-to-one, with on-to on their own, I thought I'd work out individually how to show both of these. Thank you for joining me today as we work through some proofs. I hope you learned something, that this helped you with your studying. If it did, make sure to hit that like button and to subscribe to the channel.